We come back after the tea break. So, in this session, we are going to talk about the different case studies, how they are successful and particular project. So, the first case study, Greenfield Iceland project. The location is Iceland. The target production capacity of the plant is 100,000 tons of green ammonia per year. They are using renewable energy source as a geothermal. So there are plenty of geothermal sources available. That's all. So they make that one as a renewable source for producing their electricity. Electrolyzer technology, they are used alkaline electrolysis. The estimated investment is about 1.2 billion euro. Timeline, commercial operation is expected in 2026. So you can see here from the tutorial presentation, your geothermal nothing but the energy available under the earth crust. So you are going to take out, there are molten salars are available. You can pump the water or something in that zone. Then high pressure, high temperature, superheated steam is expected out of this the molten zone. Maybe the steam is taken into the turbine for power generation. So there, the conversion of thermal energy from the steam is converted into mechanical energy in the turbine. Then the conversion of the mechanical energy to the electrical is happening by using a suitable turbine. So the energy needed for running the electrolysis plant in that plant is taken from the geothermal energy. Okay. So the geothermal energy know that the potential amount of heat available under the crust is utilized for creating the steam, which can be used for producing the power. So here they are employing electrolysis process. So we need input, output, and electrodes, the electrolytes. Ultimately, they are at the end of the electrolysis process, they are going to get hydrogen, which can be combined with the nitrogen from the air. They are going to produce the ammonia. So ammonia product can be utilized for for fertilizer to increase the crop yield. Whereas for hydrogen, green hydrogen, they can take maybe taken into the some suitable conversion methodology. They will be converted into liquid hydrogen or the gaseous hydrogen. We can use it for many applications. And hydrogen also we can carry it in the form of ammonia. So here you can see here, hydrogen carries acidities. Hydrogen also carried in the form of ammonia. So for converting this one, they are used alkaline electrolyzer. So by employing this kind of concept, we are able to ensure that the nitrogen fixation is going to be plays a dominant role in increasing the flow. So investment, what they have from the different sources, they have for the Greenfield Iceland project. So R&D market development is about 10%. Storage facility they have invested for 15%. Then infrastructure they have invested for after the 28% is invested for infrastructure. Then out of the 100%, the maximum amount goes to the electrolysis plant. 48%. Assume that the plant cost is 100 rupees. 45 rupees utilized for creating the electrolysis plant. 25 rupees goes for the infrastructure. So I'll put together 70%. Remaining 30%, I can say 15% going to be for the storage of ammonia. Then the furthermore, I can say possibility of doing kind of research or invention or innovation. There's targeted for 10%. Then operating cost and other expenditures they are using 5%. You can see here green ammonia forecast in 2026. The growth is going to be increases from because what the plant is commissioned in 2026. Then the utilization of the ammonia going to be You can see here from 2026 to 2030, increases demand in terms of thousands of tons. Almost I can say 70,000 tons they are going to produce in 2030. And 2026 about 50, about I can say nearer to 50,000 tons they are going to produce from the plant they are planned now. Maybe there may be in the future, they depend upon the demand of the fertilizer, the size of the I can say plant also going to be increases. Shipping sector, ammonia can be for shipping industries and all. They are going to they are in the need of around 20,000 million tons per year, and 2026 is going to increase to about more than 17,000 for shipping industry. That's the demand factors. All put together, you can see here, combined together, they are in the need of 140 million tons, 140,000, I can say, tons of they are going to produce it at 2030. So electrochemical ammonia synthesis of the from the presentation, what we come across from the morning session. The electrochemical ammonia synthesis is a promising alternative to the traditional Haber Bosch process, offering a more sustainable and environmental friendly approach. The nitrogen reactions is the core of this process, involving the conversion of nitrogen gas to ammonia at the cathode. Retrocatalysts play a crucial role in promoting nitrogen reduction reaction while minimizing competing side reactions like nitrogen evolution reactions. Electrolytes also influence the overall process, with aqueous, molten salt, and solid electrolytes each having their own advantages and disadvantages. Electrochemical ammonia synthesis offers several advantages, including lower energy consumption, reduced greenhouse gas emissions, and the potential for integration with renewable energy sources. Finally, the conclusions. The electrochemical ammonia synthesis represents a significant step toward the greener and more sustainable future. While challenges still persist for this method also, such as improving the efficiency and the scaling up of the infrastructure, the potential benefits of the technology make it a promising avenue for research and development. Still, R&D and a lot of role needs to be played for bringing this concept. By addressing these challenges and continuing to explore new materials and techniques, electrochemical ammonia synthesis could play a vital role in decarbonizing the production of ammonia, the critical chemical for various industries. So these are the possible questions you must have in your mind after this lecture. Compare and contrast the electrochemical ammonia synthesis process with the traditional Haber Bosch process. That's why the question was given before the tea break. What materials and strategies could be explored to address these challenges? How can electrochemical ammonia synthesis be integrated into existing green energy infrastructure? What are the economic factors influencing the adaptation of electrochemical ammonia synthesis? What are the benefits and risks associated with this technology? So now, I already assigned the work. Make a team of 4 members. The time given to is 15 minutes. Ask them to submit a chart work that should be about electrochemical green ammonia synthesis. The chart work should not contain more paragraphs. It may be a tree diagram or any pictorial representations of the concept, very short and sweet. Okay. These are the references I have used for preparing the PPT. So I thank my scholars for supporting me to prepare this PPT. So now the assignment. So you can form a team. Maybe the number of people are less. You can form 2 as a team, and you can take 15 minutes and discuss with a member and try to come up with the submit a chart work. I don't want any paragraph or something. I want only the pictorial representations of the schemes available, or I can say discussed so far. So you can draw the right diagram schematic for representing the electrolyzer, representing Haber Bosch. So all the components are already represented with you. So you can try to form some layout or something, and you can discuss what may be the idea you so far you have attained from the, I can say, 1.5 days time. now we'll move to the tutorial part.
Here they are using water. They use seawater instead.
Saline water is there.
Salt content will be there.
Yeah, the deposition is going to be there. That's why there's a possibility you can distill it out and use it. See, the systems are available. The water is scarcity. You have to design a system to take care of the salinity. Also there. But the anode and cathode, what no, there's a deposition going to be there. How to remove the scales and all, that we need to really think about. Here, right, time being, they are thinking about using I can say the potable water or water we are consuming. And maybe the later stage, people are a lot of water is consumed in the later stage. People need to think about moving towards the distillation of salt water, which can be used as the raw material. So a lot of things are there. So we need to really think about right time being there, you are going setting that, you got to use water. But some places there is scarcity of water. Then you can think about going for reverse engineering, you need to think about that. And using what is available, you need to think that yeah. So challenges. So we are going to discuss about the role of Haber Bosch for ammonia synthesis. Examine the challenges of the process modern sustainability efforts. Expected outcome. You can think about recognize the energy consumption, environmental and economical challenges, compare traditional methods to emerging green technologies. That is the thing we have given to you. So Haber Bosch, I already discussed that. So the 20th century, it was developed by Fritz Haber and Carl Bosch. So this is the person, is an industrial person, joined with the Fritz Haber, joined with the industrial person Carl Bosch. They developed the technology for producing ammonia. We are enjoying the invention of these two people, or I can say in terms of getting more real. But this person also involved in another activity at the time before the invention of ammonia. He has invented chlorine that was used for killing many Jews in World War II. So for this invention, they have got the Nobel Prize. So in general, the operating temperature of the Haber Bosch reactor is 450 to 300 bar. The temperature is 400 to 500 degrees centigrade. So it's the energy intensive process. It's actually they need to provide that heat and then the pressure to do the, I can say, the formation of ammonia. Ammonia, there are tried many catalysts, which is promoters like potassium or aluminum. Finally, come up with maybe I can say rhodium also they have tried. There are many catalysts, zirconium also they have tried. N number of catalysts they have tried. Finally, they have got a good yield in iron based FeT, Fe2O3 catalyst. For the Bosch reaction, they have utilized ferrous-based catalyst. So they are Haber Bosch was highly energy intensive, relying on fossil fuels for hydrogen production, which contributes. So for CO2 generation comes out to the environment globally, 1 to 2% only from the Haber Bosch. From 100% CO2 comes out in the environment. The Haber Bosch itself they are producing 2%. So that's why people are talking about CO2 is nothing but originally they are saying that inert, okay, but it has the potential to produce a fuel also, synthetic fuel also. You can react with the CO2 with some kind of thing, produce the alcohol also possible. And the CO2 is also having the specific which can be more than the specific of the oxygen, which has the possibility to absorb more heat from the surrounding. That's the reason why the global warming temperatures are keep on increasing. So, what are the ways in which the CO2 can be eliminated to save the environment of, I can say, the global rise in temperature up to 1.5 degree possible? If you are not able to eliminate the CO2 from these various sources, particularly for the Haber Bosch, then it will be a increasing trend happening across many places. So that's why the new concept called green ammonia or green hydrogen generation comes into the picture for eliminating CO2. From the conventional fossil fuels, normally we are using coal or the heavy oils or sometimes the methane, natural gas also used for producing the hydrogen. So now the carbon traces needs to be eliminated. One way, you can use the existing technology from coal or oil or gas to produce the ammonia or hydrogen. Eliminate CO2 by absorbing the CO2 by several sources, or carbon at the input itself we eliminate by going for water. So here as a method, we are talking about hydrogen from natural gas, the steam methane reforming method. Concept they are using for producing hydrogen from air from the PSA. The hydrogen reacts the Haber Bosch reactor at this condition. If we are missing out this condition, the ammonia generation formation is going to be not what we expected from the succeeded by the Haber Bosch process. Then after this process, some unreacted hydrogen going to be recycled back again to the input, so that will ensure that 100% conversion happening. So here it's an exothermal process. Normally we can say when you are reacting hydrogen with hydrogen, you are going to produce some amount of energy is going to be comes out. Then it's possible to utilize that energy. It's going to be not going to be utilized for the process. Then that system is not going to be considered as a good system. Any videos?
This plant makes 800 tons of ammonia every day. That's enough to fertilize 7,000 football fields. It uses a system called the Haber process. The process needs a giant maze of twining machinery and hissing pipes. To make ammonia, they must first make its ingredients, hydrogen and nitrogen. This is where the nitrogen comes from. There's not much to see on the outside, but on the inside, the machinery pressurizes air to separate out nitrogen from all the other gases around it. Inside this tower, the different gases turn into liquids at different temperatures. It's called fractional distillation. Half a kilometre away is a vast furnace. It makes hydrogen from natural gas, methane. Methane has the chemical formula CH4, 1 carbon and 4 hydrogen atoms. They extract the hydrogen by mixing the methane with superheated steam, H2O, at 500 Celsius. The tremendous heat splits up the methane from the water molecules and frees up the hydrogen. What left over is carbon monoxide. Oxygen and hydrogen come side by side down these pipes. Part of the plant where ammonia is made is called the converter. Just like the experiment in the lab, the converter contains iron for a catalyst, and it's hot. And it's at such high pressure that the metal wall must be made 11 centimeters thick. Outside, enormous steel bolts hold it together. Here's the problem. High pressure and cool temperature would make lots of ammonia, but it would take too long. So they have to keep the reaction up. That makes it go faster, but it also makes the ammonia break down quicker. Somewhere in between, there's an optimum, a temperature and pressure that works best. So the final stage of the plant starts with a compressor. Pressurizes a mixture of nitrogen and hydrogen gas to about 200 times atmospheric pressure. But the compression has another effect. It also forces the temperature of the gases up to about 350 Celsius. That makes the nitrogen and hydrogen gas molecules split up. Inside the converter, a hot iron catalyst is waiting for the nitrogen and hydrogen. They react together at its surface to make ammonia. The reaction also releases heat, keeping the temperature just right for maximum production, about 500 Celsius. But even so, some of the nitrogen and hydrogen is still left over. So the mixture that passes out from the converter isn't pure ammonia. The very last stage chills the mixture's temperature down so that ammonia condenses out as a liquid. It's drained off from the bottom. Meanwhile, the nitrogen and hydrogen float up to the top and get sent round a loop back to the converter.
So, to make ammonia from the air by the Haber process, air is first liquefied under pressure, and the nitrogen is separated out by fractional distillation. Hydrogen is extracted from methane at high temperature. The nitrogen and hydrogen are combined to make ammonia. This is done at high temperature and pressure with an iron catalyst.
So high energy consumption levels are used in Haber Bosch, but also they mentioned that in the video, it's an exothermic process. So we need to ensure that the temperature should not exceed more than 500 degrees centigrade. So normally, the hydrogen and nitrogen goes with high pressure of 200 bar, maybe 150 to 300 bar, and attain the catalyst bed by getting a temperature of 500 degrees centigrade, 50 to 500 degrees centigrade. So then only the reaction is going to be converted. So there are many Haber Bosch process notes. People are talking about that and what the problem associated with the Haber Bosch concept and what may be the problem and who also involved in the what may be the effect going to happen to the humans. So they will discuss that. So there are different case studies, right? It's available. You can able to explore
The dusty desert of Saudi Arabia for around
case study.
the incessant heat, and right in the middle of it, the replay of a world record. The single train ammonia plant with a capacity of 3,300 metric tons per day. Design, ThyssenKrupp Uhde. Unusual environment, unusual dimensions, unusual circumstances. For the ThyssenKrupp Uhde team, it's business as usual. It was the Samsung engineering company of Seoul that was awarded the contract for the turnkey construction of the plant. However, the client, Saudi Arabian mining company Haber, insisted that ThyssenKrupp Uhde should supply the process, basic engineering, special equipment, and the specialists, because only the Uhde dual pressure process permits single train capacities of between 3,000 and 4,000 tons of ammonia per day, and Haber wanted a minimum of 3,300 tons. Starting up the plant slowly is routine for the engineers from Samsung, ThyssenKrupp Uhde, and the client. The higher pressure part of the synthesis unit is already on stream. 100 tons of ammonia run into the gigantic tanks every hour, over 2,200 tons a day. Now, the second part of the unit is due to start up. Another 1,100 tons produced at lower pressure. Incidentally, the ThyssenKrupp Uhde engineers are dealing with a specialist who first worked with Uhde 30 years ago on the construction of an ammonia plant in Brazil. This induces comparisons between then and now, quite apart from the improvements in plant performance since 1981.
At the time, it took us months to produce ammonia. It's nice to see the evolution of the design. And here in Saudi Arabia, the largest ammonia plant in the world, we are able to achieve this together with Samsung and Uhde. I startup period of only 6 weeks. And as of today, we are producing ammonia.
Underneath the OT reactor, the specialist from ThyssenKrupp Uhde's partner company, Johnson Matthey Catalysts, has erected a small laboratory. For safety reasons, the temperature and relative humidity are measured at several points, because the catalyst in the reactor has to be carefully reduced with hot hydrogen, layer for layer. an exercise in patience that has to be interrupted time and again if the reaction doesn't work. A perfectly normal procedure when starting up an ammonia plant of this type. The same happened a few years ago, only an hour's drive from here. ThyssenKrupp Uhde built the first plant based on a dual pressure process for Safco, the Saudi Arabian fertilizer company. 3,300 tons of ammonia per day. The adjacent urea plant produces 3,250 tons per day. In contrast to Safco, Malan subsequently feeds the ammonia from the plant built by Samsung and ThyssenKrupp Uhde into a giant fertilizer complex comprising sulfuric acid, phosphoric acid, and 2 diammonium phosphate plants. Routine, fine-tuning. In the ThyssenKrupp Uhde steam reformer, tail gas from the synthesis unit is slowly mixed with the natural gas for firing. Flames become more uniform. Energy efficiency improves. Lower exhaust gas values help protect the environment. ThyssenKrupp Uhde, engineering with ideas.
So Saudi and they already producing 3,000 tons per day. China also, they are, I don't want to show the videos and other things, but as Norway, Japan, and many places they have installed the system they're successfully producing. With respect to Haber, Bosch, right? And as we engineers are doing research in this area, maybe we can also think about how our research maybe contribute for producing ammonia in some other way what Haber, Bosch. Okay. So I request everyone, please address your ideas, convert it into form of your schematic, and that will be discussed for another 10 to 15 minutes. So everyone come up with their idea and it was commercialized also. And as we people doing some kind of research or interest in this area, we can also think about how our plan should be, what may be your ideas in producing hydrogen, what Reddy already pointed out. So there is a possibility to use the saline water. So if the saline water is there, then nobody will object to you. Time being, we are happy that the drinking water or the distilled water can be used for producing the hydrogen and can be converted to ammonia. But later stage, there is a food versus I can say invention will always come. In this case, people will not allow you to use that water for producing hydrogen or ammonia. So we can also think about that perspective and bring our new inventions by bringing the material which is not at all going to be utilized for, I can say, producing hydrogen. We request someone and discuss with the team, the participants. We one or two can come and discuss. So based on the discussion, different case studies you come across, yesterday tutorial and today's tutorial. So what may be your idea? What may be your idea in proposing the system? And by taking different raw materials into account, so what is your way of starting the research? We can make use of the board also. Someone can make use of the board also. Or someone wants to deliver, I don't want more, I want to talk in terms of, I can say, some presentation you want to do it, or we can also do it that way. What may be your raw material? So you can tell me what may be your raw material, we can use it. So whether you are going to accept the green technology for producing ammonia, or I want to keep the Haber Bosch, which is proven one, and I want to eliminate CO2 in a better way. So I need some different times.
we can use in like this vegetable wastage. Like in Hyderabad or Chennai, big cities, there is big market yards. If we saw at the evening time, there is a lot of wastage. So we can use that market waste and we can produce, we can generate that from the nitrogen.
No, so you are going to get different vegetable waste. So what you want to convert the waste into?
That waste into biochar and this.
Ultimately, we need hydrogen.
Hydrogen.
Hydrogen to nitrogen. Hydrogen, okay. Hydrogen, how do you produce it? Not a conversion method of electrolysis or steam methane reforming. Is there any idea or if you have gone through any literature and for producing the hydrogen apart from the electrolysis or steam methane reforming?
Then the salt we can use, salt water we can use by using the solar energy. Now they are in some people they are installing plants. They are converting the salt water to water. So they are using conventional method. I think so we can use the solar plants and with the power we can.
So now the system needs to be operated continuously, right?
Yes,
So if the water is there, I can pump it. So if you are going for saline water, producing the water, and it needs some time, right?
yes, sir.
So to produce, suppose you are loading 1,000 tons per day, saline water to convert into the water which can be used for electrolysis. So what may be the conversion? How much the time you need it? But what is the, do you have any idea about using the solar PV and the hybrid technology where the solar PV along with the distillation system? Do you have any idea? You have come across any paper?
They are using.
One thing is we are using saline water,
Yes, sir.
distillation. But can we use a hybrid system for producing electricity and also producing water? In a single system?
Once it comes, PCM they are using, but with that PCM also there is a problem. But once it convert to solid, and it will take time to convert to liquid also. So liquid and solid conversion. So if you want, we can't produce continuously.
Is there any other method of storing hydrogen other than storing at a pressure of 350 bar or 700 bar or converted to ammonia? Is there any other way of storing hydrogen? As a side hydrogen separately or in the form of compound? If you want water, suppose you breaking the water, you can get oxygen and hydrogen. So water has both hydrogen and oxygen. Similarly, can you able to convert the form of hydrogen other than the ammonia? You can also get hydrogen from that. Ammonia is nothing to storing hydrogen, right? So is there any other way the ammonia can be used for storing the hydrogen? Similarly, is there any other compound you can able to produce it to store the hydrogen?
Sodium hydroxide plus aluminum make
Sodium?
hydroxide plus aluminum will make sodium aluminate, which will produce more hydrogen than the normal.
The OH component, right? So from the OH component, what may be the expected operating conditions for it?
It's around 50 to 60 degrees because it's a exothermic reaction. We don't need any extra.
OH along with
The sodium aluminate.
sodium aluminate.
Which can be used for the zeolite. For zeolite means production of oxygen for medical purposes.
Okay, okay.
We can purify to, we can make a very good oxygen from that. So we can make the byproduct from sodium aluminate, which is the aluminum zeolite. It's called.
You are talking about oxygen or hydrogen?
No, hydrogen.
Hydrogen.
First we have to synthesize from sodium hydroxide plus aluminum. That means we can get the aluminum from any scrap or something like that. Any material, which around comes from around. I think today.
You need a reactor to.
Nothing, sir. Nothing is there. Just a sealed container.
Container,
Yeah, we have just steel containers.
steel container, okay.
Or ceramic containers has around 100 degrees Celsius, which can be done. Because when we react sodium hydroxide, which is around 4% to 1% of aluminum, that means 4 kilogram of sodium hydroxide plus 1 kilogram of aluminum, we will get it's an exothermic reaction. It will react.
But what may be the hydrogen generation rate?
Yeah, it will be around, for example, I have one picture. Around 2 kilo of aluminum and 4.3 kilogram of NaOH, that means hydrogen, sodium hydroxide. We can get around 2 kilo of hydrogen.
But how much the quantity you need to consume when you compare with water?
Water is very low because, for example, you can have just like a lithium cell, power to weight ratio is very less. Comparatively, with the only for 1 or 2 kg of aluminum, it will be cost volume will be very less. And even we can go for a very scrap material, very narrow powders or something like that. It will be very reactive.
Is there any proven concept for that?
Yes, sir. We highlight for me. I have done a research.
Okay.
Because I have tried a lot of systems. I have done that. It's very helpful also. Even I have done the engine also. So it's
Run it to the
hydrogen, purely hydrogen.
on the engine.
On engine.
Is it petrol or diesel?
Diesel, sorry, petrol.
Is there any modification you need to incorporate?
That is not more over, but there is some issue with that hiring issues. This would be.
What may be the purity? What may be the purity of hydrogen?
I think it's. I don't have any apparatus or something like that. But I think it will be around 90-80% because there is no any other.
Something like falls under alkaline electrolyzer something.
Yeah. It's the same like alkaline electrolyzer. Because the byproduct is sodium aluminate, which is some material from zeolite. We can use for anything for oil purification, for transformer oil purification, and the diesel purification.
But in that the proposed thing you are saying that it doesn't need water.
Yeah, 100%.
We don't want.
Yeah, we because NaO which automatically is come around water only.
Okay.
But 1 kg of NaO will need 10 liters of water. It can be any water, no issues. And one thing, so with the same using of this technology, we can use steam also because it's an exothermic reaction. We can get the steam, temperature from that. We can make it steam and water to distillation, sewage water distillation or something like that. We can get, and even though we can, if you use a Peltier model or something like that, we can make the power also.
But you need some kind of energy input, right, to do the reaction.
No, sir, nothing, sir.
No need of any.
No need anything, sir. Just for example, we can have.
How you are maintaining temperature? You set some temperature.
So it's an exothermic. Just like how to add the quantity. That's all. But at certain time there will be our saturation temperature. Saturation will be there. Total aluminum or any should be control. Sorry, it will attain on the temperature, and we have to rearrange the.
So anything from anybody? Have any more idea?
Sir, we are using coal for the production of the hydrogen, sir. My concept is we can use gobar gas, sir, because during gasification, SO2 emissions are higher in coal, sir. And fly ash is the main problem in coal residues, sir. This can be avoided by using gobar gas.
Ultimately, the gobar gas contains high amount of methane, right?
Yes, sir, but the
It's like you are doing the information of natural gas.
yes, sir.
Only thing is not come from conversion, it comes from the waste.
But the heating energy gasification process is higher, sir. That energy can be used for other uses. Because
You are talking about biogas, right?
coal, sir.
Yeah.
Coal converting into methane, we have high temperature.
Yes.
That energy can be avoided using natural gobar gas because it is a time consuming process. You can't get instantly. It takes timing, sir, but the slurry can be used for fertilizers in organic fertilizers. That's the.
Well, our question is there any nitrous elements are there in the bio, that powder or whatever?
Yes, sir, we can separate the uric acid, sir. From the urine, we can separate, sir. Urea has nitrogen, sir. But that process, I don't know how to.
Deals with the purity.
Purity.
That is the main.
Purity and the
If you
ratio.
are using the hydrogen for some engine application or for a boiler, no issue at all. But when you are going to use it for fuel cell, particularly you want to produce electricity, I can say, in the automobiles, right? Then the purity 99.9% nitrogen is not right.
So that ratio is lower, sir, in urea, uric acid, nitrogen.
Any more ideas, please?
We have done the project on plasma process for the water treatment, sir. That is
Heating
the
gasification.
process for water treatment. We have tested for the different water contaminants micro.
Plasma you are using for
Plasma process for water treatment, sir.
water.
Yes, sir. Within a 20 minutes itself, we could observe that all the microbial species have died. So all the mineral content acid is there. Like that only. Also, we have tested for the hardness also. Hardness reduction also somewhat reduced due to the plasma process. As well as some of the organic and inorganic contaminants also we have tested, sir. All the contaminants, so it's further removed, sir. So we have concentrated on developing the reactor. How we are focusing the achieving the high.
It means you are going to treat the water that is already drinkable water.
Yes, not drinkable hardness from contaminant water, sir.
But how the plasma is used for removing the water?
Yes, sir. During the plasma process, as you said yesterday, also lot of ion species were formed. So in that, if we are going to use the nitrogen as the gas, so nitrogen, if we are going to use the air as the gas, so oxygen and nitrogen is there. It will going to ionize, it will form as a hydroxyl and hydrogen peroxide some hydronium ions. It will responsible to degrade the water contaminants present in the water. That's what the main concept here. So after the treatment also, we could observe that if you are extending the treatment time, finally we observe that water pH is drastically reducing, sir. That is in the acidic pH within a 15 minutes itself, sir. From that, we came to know that we concluded that more amount of nitric acids or nitrogen based, like NOx and NO minus this kind of species which is present, which is appeared due to that only water acid peak. It's going to be like the 3 or something, sir. So from that, I have concluded that nowadays people were concentrated on that to produce a nitrate based water using the plasma process as a fertilizer Okay, sir. So my concept is to get the nitrate from the plasma process by optimizing the reactor water else configurations. That nitrate we can go for the electrolysis, photoelectrolysis, sir. So we can go for the photo means solar light. So we need to develop the electrocatalyst as the which is utilizing the sunlight, like the visible light. So we have to focus the 3 things area, like one is the plasma reactor development for enhancing the nitrate generation. Next, through photoelectrochemical process, we are going to reduce the nitrate in the ammonia. Whether it may be ammonium hydroxide, whatever bicarbonate is there. So for the electrocatalyst, we need to concentrate that. We want to utilize all the solar light. So we need to develop the electrocatalyst that should be in the visible light. That should have the more.
What is the operating parameters for the photo?
Yes, sir. Actually, photo operating parameters, we should develop the tactical one of the visible light than that of the UV light. So only 20%, 45% of visible light is available. We have to enhance the visible light utilization efficiency of the photocatalyst. So in the electrocatalytic part, we need to develop the catalyst. We should have the more absorption in the visible light utilization efficiency. So we can more efficient. So from the NO2, which is getting from the nitrate, from the plasma process, that we are going to reduce through the photoelectrochemical method. new scenarios. So nowadays, hydrogen generation, they are proposing to develop the photo electrocatalysis method for enhancing the hydrogen yield. So we are going.
What may be the time in which we can able to put it? So the process we can able to generate the hydrogen, right, within a fraction of a second, right?
Yes, sir.
So order.
Sir, nowadays, for 1 point.
Okay.
இல்ல இல்ல போன் கிட்ட வச்சு
Sir, I never involved in this project on hydrogen generation, sir. My aim is to, through plasma process, we can able to generate the nitrate. From the photo electrocatalysis process, they are going to achieve the high amount of hydrogen generation. So, in that, we are supplying to the nitrate into that process. So, we can enhance the, through this way, we can improve the, like, produce the ammonia, sir. That is it. And also one more concept is that is the plasma electrocatalysis. So both the things is happen in the same reactor, sir. Like both the plasma process as well as the electrolysis process happen in the same.
That's the thing we are.
Yes.
The thing is, we are dissociating in the water, then the generation of ammonia, the same thing. That's why I said the engine, right, we are converting fuel into thermal energy, then into what happening in the single system. So we are having the reactor, plasma reactor, which can able to dissociate water into hydrogen, then reacting with the plasma ionized gas nitrogen form ammonia.
So other species and all, it's having the lifetime is very short than that of NOx. This is like hydroxide and hydrogen peroxide is having a short lifetime. It will go immediately. So only when the nitrogen ions and hydrogen ions present the solution, that's what the pH of the water is acidity is there. So we can use that water for producing hydroxide for the photo electrocatalysis. That is what.
So ultimate aim here is producing ammonia, not for fertilizer. The theme here is producing ammonia for storing the hydrogen. In that case, the purity of hydrogen comes out from the ammonia, plays a major role in taking into the fuel cell application. Because the EV charging and all is going to be an issue in the near future. People are thinking about carrying the hydrogen in a better way, dissociate in a better way, get the high purity which can be used for fuels.
Your raw material is a wastewater, sir. Both the things we can achieve simultaneously. So treatment of the water as plus we are going to generate an nitrate from the wastewater.
Any more suggestions?
சரி இப்போ அக்ரிகல்ச்சருக்கு வந்து யூரியா வந்து நிறைய போடுறாங்க சார். இப்போ அம்மோனியா ப்ரொடக்ஷனே வந்து 70% மேல வந்து ஃபெர்டிலைசருக்கு தான் சார் போகுது. நீங்க வந்து கார்பன் டை ஆக்சைடு வந்து ஃபுல்லாகவே குறைச்சிடுறீங்க. பட் வந்து NOx-லாம் அது இல்லை சார், நைட்ரஸ் ஆக்சைடு. கார்பன் டை ஆக்சைடை விட 300 மடங்கு ரொம்ப டேஞ்சரஸ் ஆனது. 114 வருஷம் வந்து இருக்குன்றாங்க. அதே மாதிரி அதுக்கு ஒரு ரெமடி வந்து நம்ம ஆக்டிவேட்டட் கார்பன் போடலாம் சார். போனோம் அப்படின்னா ஸ்லோ ரிலீஸ் ஆகும். இப்போ ஆனால் கவர்மெண்ட் வந்து நீம் கோட்டட் யூரியா பண்றாங்க. பட் அது அந்த அளவுக்கு ஒரு இதா இல்லை. அது எதுவுமே போட்டாலும் யூட்ராஃபிகேஷன் பிரச்சனை, அப்புறம் வந்து கிரவுண்ட் வாட்டர் வந்து ஹெவி மெட்டல்ஸ் பிரச்சனைலாம் இருக்குங்க சார். இப்போ பஞ்சாப்லேயே வந்து அந்த ஹெவி மெட்டல்ஸ் இன்ட்ரூஷன்னால கேன்சர் வரதுலாம் அதிகமாக இருக்குது. கேன்சர் ட்ரெயின்லாம் பார்க்குறோம். ஃபார்மர்ஸ்ட இருக்கிற பிரச்சனையும் வந்து மிஸ்மேனேஜ்மெண்ட் தான் சார். ஒரு ஏக்கருக்கு வந்து 1/2 மூட்டை யூரியா போடணுன்றாங்க. பட் வந்து 2 மூட்டை 3 மூட்டைலாம் போடுறாங்க. 35% தான் சார் வந்து பிளான்ஸ் எடுத்துக்குது. இது எல்லாமே வந்து வேஸ்டா போயிடுது. இப்படி போறப்ப நைட்ரஸ் ஆக்சைடு வந்து ஒரு மிகப்பெரிய பிரச்சனை. மேபி ஒரு 6% மட்டும் கிரீன் ஹவுஸ் கேசஸ்ல இருக்கிறதுனால அது ஏதோ கன்சர்ன் பண்றதுன்னு நினைக்கிறேன். பட் அது வந்து ரொம்ப பெரிய இஷ்யூவா இருக்குங்க சார். அதுக்கு வந்து நம்ம பயோமாஸ் பைராலிசிஸ் பண்ணி நம்ம ஆக்டிவேட்டட் கார்பனோட கொடுத்தோம் அப்படின்னா அது வந்து ஆனா எப்படி பார்த்தாலும் காஸ்ட் வந்து கொஞ்சம் கூட தான் சார் இருக்கும். ஏன்னா யூரியாவுக்கே இப்போ 1,50,000 கோடிக்கு மேல வந்து கவர்மெண்ட் வந்து ஃபண்டிங் பண்றாங்க. அது போக எப்பயும் கொஞ்சம் இதா இருக்கும். அதுல ஏதாச்சும் ஒரு டெக்னாலஜி வந்துச்சுன்னா நல்லா இருக்கும் சார்.
You need to think about that. You have some, you identified a problem, so nobody will come forward to solve your problem. You can solve your own problem by bringing the right people in your team. The idea is good. Idea is good. You are saying that convert it into activated carbon. Fixation is going to be what is needed, and amount can be utilized. So the extra thing need not be that awareness, right? So ultimately, the rise in temperature happens not from the nature, not from the humans. So we are we are going to, we can say, pollute the environment like anything, and we are also trying to find out some, I can say, solution for solving this problem. What damage happened is happened. So we need to make use of that, I can say, utilization of the plastics and other things. How many of them are still we have the habit of carrying the bag when you're going for the I can say shopping mall or going to the grocery shop or going to the beach shop? No one. For he's carrying one meat, you're asking 2 plastic covers, right? Then you're asking a few more to, I can say, the weight is more, then keep on this increasing, right? Very close.
சார் ஆக்டிவேட்டட் கார்பன் பண்றதுக்கான எனர்ஜி அதிகம் சார். நீங்க அதுவும் பார்க்கணும்.
இல்ல அதான்
அதாவது சாம்பல் எடுத்து போட்டு சொன்னாங்க. ஸோ இனிஷியலி வி யூஸ் டு புட் சாம்பல், தட் இஸ் ஆல்சோ ஆக்டிவேட்டட் கார்பன் ஒன்லி. நீங்க ஆக்டிவேட்டட் கார்பன் பண்ணா ஒன்றும் இல்லை, சர்ஃபேஸ் ஏரியா இன்க்ரீஸ் பண்ணி போடலாம். பட் ஆக்டிவேட்டட் கார்பன் பண்றதுக்கான எனர்ஜி எந்த மெத்தடாலஜி அதுவும் பார்க்கணும். இப்போ நம்ம அல்டிமேட் எய்மே வந்து எனர்ஜி குறைக்கிறது தான். ஸோ ஒன்லி வி ஆர் டெல்லிங் அபவுட் கோல்டு பிளாஸ்மா எவ்ரிதிங். ஸோ if you want to get activated carbon, you have to use high energy. So we have to consume, or we have to think about the energy consumption and also the profit. Because
you can suggest a good method of using. No, we are not criticizing you. So ultimately, we are not to solve one problem. So consuming electricity from grid also, you are consuming more fuel to produce the electricity. More CO2 is coming up. More oxides of nitrogen will come up. So you are saying that not NO components, right? Something like this, right? But yeah, when the temperature during the reaction exists more than 700 degrees centigrade, the air contains 79% nitrogen, right? Reacts with the oxygen, produces oxides of nitrogen. So what way you are making use of that energy? That's why we are saying that go for a green method to produce the electricity. That electricity you can use it for what is the method you are going to propose. Don't depend on the electricity going to be provided by the government of India. You produce your own thing. Even if you want to start a company, you must have the renewable base. Nobody will question you. So solving one problem, creating another one, is not going to be acceptable. Balance. You produce CO2 more on your plant. At the same time, you need to consume it also. So plant more trees, so that CO2 is going to be absorbed. That's why people are saying that plant more trees. Even you can see that in Trichy, right? The construction happening, the engineers. Of a plot, no space for moving. Right? If you open the window, it's going to hit on the other's house. No movement for air, no plantation, nothing is there. Then automatically you are increasing the CO2 level, and that's so.
All the trees were removed.
If you go to Denmark, you go to Norway, well planned. You cannot design your own house. That is a problem in US and the UK and all European. The plan was to be there for particular place. This is the plan. Because a billionaire, you cannot design your own house. Each house has the ventilation facility, tree plantation, right? Everything needs to be provided. All the bathroom water, the backward water, whatever the water that you are using, right? Kitchen waste, water, everything. It has to be properly treated, and only you can see that in our house, right? Whatever the waste comes out, vegetable waste or any waste, to find out where the space is available. Nearby your house, any empty plot is there, you will throw it away. Right? That is going to have some vegetables or rice or something like this there. Then I can say cow or other things will come and consume along with the plastic goes inside. You are drinking the same milk.
சார் அதாவது நீங்க சொன்னா கரெக்ட் தான் சார். பட் இட் இஸ் லைக் கிரே அமோனியா. we should go for green ammonia. Our ultimate aim is using renewable energy.
So the concern is okay.
இல்ல சார் நான் அம்மோனியா ப்ரொடக்ஷன் ஓகே இது வந்து குட்டு நீங்க அடுத்த கட்டத்துக்கு போறீங்க பட் அதுல இருந்து யூரியா ப்ரொடக்ஷன் பண்ணதுக்கு அப்புறமா வந்து நைட்ரஸ் ஆக்சைடு வருது இல்லைங்க சார் அதுதான் சார் பெரிய பிரச்சனை கார்பன் டை ஆக்சைடோட 300 மடங்கு ரொம்ப டேஞ்சரா இருக்குல்ல சார் அதுக்கு வந்து சொல்யூஷன் நீங்க சொல்லித்தர நல்லா இருக்கும் சார் அதுதான் அதுல எனக்கு தெரிஞ்சது இப்போ ஆக்டிவேட்டட் கார்பன் போனோம்னா மேபி ஸ்பீடா வரத நம்ம வந்து கொஞ்சம் கொஞ்சமா கொடுத்தோம்னா பிளான்ட் அப்சார்ப்ஷன் நல்லா இருக்கும் இன்னொன்னு என்னன்னா நம்ம யூரியா போடுறதுனால வந்து ஸ்பீடா வந்து கிரீனிஷ் ஆயிடுச்சு சார் அதனால வந்து இன்செக்டோட இன்ஃபெஸ்டேஷன் வந்து ரொம்ப இருக்கு சார் ஸ்டெம்போரர்லாம் வந்து அந்த அதோட அடல்ட் வந்து எங்க முட்டை வைக்குமா எந்த இலை நல்லா கிரீனா இருக்கும் அங்கதான் வந்து எக் வைக்கணும் சார் அதனால நம்ம அந்த அதுல ரிலீஸ்ல வந்து நம்ம ஏதாச்சும் அடுத்த கட்டத்துக்கு போகணும் சார்
Controlling all other things except the growing. That needs a lot of
ஆனா இன்னொன்னு வந்து நான் வந்து பிராக்டிகலா பார்த்தது வந்து ட்ரெடிஷ்னல் ரைஸ் வந்து யூரியாவுக்கு ரியாக்டே பண்ணல சார் போடுறதும் வந்துதான் போடாததும் ஒண்ணுதான் பட் நம்ம ஃபுல்லாவே ட்ரெடிஷ்னல் பண்ணாம ஸ்ரீலங்கா மாதிரி இன்ஃபிளேஷன் போயிடும் பட் நம்ம we can manage.
Sir, they have ultimately stopped ammonia, sir. That is urea. Sri Lanka ultimately dropped. So they didn't give time. So, we have to do it regulations. So, like green farming. Green farming also we have to make some certain process because we have made the soil. Sir. So we need some we have to do some reworks in that, sir.
Any more ideas? More, please. This is a question and answer session, and ideas also will come. So we will be giving ideas better than what I have in mind. Ideas only, but we are not going to take your ideas. Much ethics also. But somebody is giving good idea, you cannot use it in your research. So this is their brain behind that. So we should appreciate that. We can leave them. So don't take it. Madam is suggesting some plasma concept for water or something, right? So we have the plasma reactor. We don't want to try that. Should not try it. I'm telling you, should not. Anything comes from the research, you should throw it out from the lab. So that is the thing I'm telling my scholars. You do research, but don't take others' information, but you can recruit the help for them. This is the thing you are working. I want you to take the facility. But some contributions will be given in form of a joint patent or joint publications or joint project in future. That is possible. But don't take their idea. Just his idea. That ethical thing everybody must. Please move.
Thank you, sir. So whether the ammonia can be used in automobiles for propelling engines?
Yeah, we can try.
So in that case, what might be the fuel? I mean, instead of LPG or something, what?
Yeah, this is why in the yesterday's presentation we have discussed the energy density. So how much per kg of fuel we are going to use? Hydrogen leads that. And next to that, the LPG and other things will come. But ammonia is a potential fuel. That's why we are saying that. In order to remove the diesel or petrol to eliminate CO2 in the near future, we need to really think about the fuel which is free from the carbon. So we are going to test it. So Saravanan is going to test that one. This also is a consumable only. Right? It's a fuel is going to create some energy actually. You burn it. It's toxic, but we need to take care of those things in account. It's a very good flammability also there. Flammability index also there. But ammonia having high ignition temperature, I think so. So we cannot use that engine or fuel, maybe in diesel or something, some modification. But all the things we need to explore it. But ammonia, a lot of research people also available. Research papers are available. They use ammonia for running engine. That's just. But compared with the energy density of diesel, I think it's not comparable. So we need to accommodate. Suppose we are giving 1 liter of, diesel. It's going to be 10 or 15 liters of ammonia to match the energy level, what we needed for creating the power. That is the area we need to explore. We need to strengthen the ammonia energy value by hydrogenation or some method we can do. Some research is going on, but I am not, I didn't touch on that. We are success in producing ammonia from the plasma reactor. So, and also we have, I can say, eliminate the other gases from the, I can say the total product comes out. So we have segregate the ammonia and it is working on, it's stored in the form of liquid now. So the purity also we need to work on it. We need to take that fuel. Is there any method to purify the ammonia a little higher so that the energy density can be increased by adding some other, I can say, solvents or something, which can boost up the energy density. That is the thing he has to explore.
There is there any storage problem?
I think, Saravanan, you can give the answer. You have any storage problem?
Storage.
Yeah, we are storing. No, we are storing it. We are having a freezer. So we are converting it and we are having a low temperature freezer. In that we will be storing some quantity. So whenever we are in need of fertilizing it, we will make use
No,
of
what's the question is, you are storing at -33. Okay, that is the method, that's temperature we are waiting for. Separate out the ammonia from
Yeah.
the products comes out from the reactor.
Yes, sir.
His question is whether it can be used ammonia at atmospheric temperature as a liquid.
It's a liquid. No, we cannot use.
But when you go for commercializing, so that refrigerators, that cost will be more when compared to raw. Yeah.
His question is, you are separating out in the form of condensing it, right?
Yes, sir.
Can you use it as a liquid or inject the fuel directly?
So we can be use it as a liquid, but the storage temperature can be maintained in such a way that can be used as a used for the respective application. If we are going to use for any automobile vehicles, now accordingly we can use it as a gas. Sir. We need to again bring it.
Yes, if you bring the gas to ambient pressure and temperature, it still exists in liquid state or gas state.
We convert to
Gas state only. Sir.
-33 only.
We can store it because when we are bringing it, converted into liquid, it will be having more energy content than the gas form. So whenever we are using an automobile, we are working on it. We can use
normally the hydrogen
liquid
storage, the lot of 350 bar or 120 bar. But here you can compress it, bring it to ambient, compress it to 10 bar, 10 to 20 bar. So then you can store it comfortably.
Yes, sir.
That is the biggest advantage. So rather than carrying the heavy bomb, hydrogen bomb in the cylinder in the engine, then people will think about somewhere is going to explode whenever the hydrogen gas find the required ignition temperature.
when it is in a liquid, so 10 bar is enough. We can store at 10 bar or -33 degrees. But when it is being a gas, it can be used in an atmospheric.
So the big cylinder, is it possible to store in a cylinder,
Which one, sir?
like well filled cylinder?
We can store there actually. We can store, but it will be in the form of gas.
But we
If
need
you
some
want-
kind of energy to be given to maintain that as to store it in this.
Yes, sir.
So other areas we need to explore it actually.
We have to-
We are producing ammonia, then we are -33, we got the liquid.
If car also you want to use means that someone separates it
In the form of liquid, our work will be very much appreciated. So how to take the ammonia in liquid form, similar to how we are carrying the petrol or diesel, it is a real challenge.
Yeah, we should close the session, sir, because 1:30 sir will come correctly.
Maybe we'll discuss
Discuss
during
it.
that, we'll discuss during the lunch. So it's close to near.
In the material for reactive ammonia, which material of more ammonia?
Material. Normal LPG cylinder is there. Like that.
Maybe we'll take you to the lab when